Hello everybody and welcome back. Today we're going to be talking about Magic Pocket, which is a technology out of DropBox. Now for those of you who are like, I've never heard of that, why the hell would you talk about it? Well, the idea is it's pretty similar to something like S3, and since S3 doesn't have any papers talking about how it's built, hopefully this gives us a little bit of insight. I also think it's pretty entertaining that it's called Magic Pocket. You've got a lot of good software out there like Debian, named after the guy's girlfriend. You've got Lucene, named after the guy's wife. MariaDB, named after his daughter. Magic Pocket, he just named it after his fleshlight. So clearly the guy who created this at Dropbox is a very inspirational gooner, much like myself, and obviously I have to pay tribute to him by making a video on this piece of software. Okay, welcome back everyone. Today we're going to be talking about Magic Pocket, which is, I guess, created by Dropbox in about 2016. They've got a bunch of articles on their tech blog, which I'm basing this off of, as well as one long YouTube video that kind of summarizes all of them. So this is basically a blob store. For a while now, I've really been looking into how something like an object store actually works in practice. And there are quite a few articles, or I guess, scholarly articles devoted to how to make something like Hadoop, like a distributed file store. But this is a blob store. And so S3, Microsoft, and Google don't really have anything detailing how they make theirs. But fortunately, Dropbox gives a lot of details on it. And at the end of the day, they do store a lot of files. That's kind of their whole business. So I am very much willing to learn from them. Apparently, Facebook also has an article on this type of thing, but whatever, what can you do? So let's go ahead and use the Dropbox one, and we'll talk about that. So basically what they're trying to do here is they want to maximize the amount of storage that we get out of our hard drives. We also want to maximize the durability. We can't have files getting lost all of a sudden, no matter what the type of weather situation is or anything like that. And to ensure this, they do multiple different types of, ensuring durability of files, right? Maybe they'll do normal replication. Maybe they'll do erasure encoding, which we'll talk about later in this video. Maybe they'll do stuff with geo-replication and try and make that less expensive as well so they can store more files per dollar. And then maybe they're even using different hard drive technologies in order to be more efficient. These are all things that we'll talk about in the course of this video. So basically, in terms of the simple API of Magic Pocket, you can do puts, and you can do gets, and technically you can do deletes as well. But basically, all that Magic Pocket is doing is it's storing a bunch of 4 megabyte blocks. So you can think of blocks as chunks of a file, right? So even when you're a user and you're operating on a Dropbox file, maybe you make some changes to the file. Those changes are going to be reflected in terms of a few 4 megabyte blocks. You'll put those in the block store. You'll have some sort of metadata elsewhere in Dropbox that's referring to those, and then you can basically recreate a file from all of these different 4 megabyte blocks. So once we have a block, what we'll actually do in Magic Pocket, I'm going to try and introduce all the terminology here pretty early on, is we'll place a block into a 1 gigabyte bucket. So buckets are going to be the unit of replication within Magic Pocket because we move around one bucket at a time in the event that we need to, say, re-replicate something because maybe we don't have all the replicas that we need for it. Maybe we want 3, but there's only currently 2 replicas. So a bucket is the unit of replication, and the term for all of the buckets on multiple different physical storage nodes is known as a volume. Thing to note about buckets in Magic Pocket is that they are append only. This makes the system a lot simpler. There are a lot of design choices that they make throughout the paper where maybe they're not necessarily the optimal design choice for performance, but they are the optimal design choice for maintaining simplicity and allowing the developers on this team to make this system as easy to use as possible. And so being append only is very much one of those things. You basically put blocks into the bucket until it's full. Once it's full, that bucket is considered closed. It can no longer be modified whatsoever, and it's replicated as it should be. It should also be replicated when the block isn't full and we're still appending to it, but once it's full, it's immutable, and so then you have some extra tricks that you can do there to make things a bit more efficient. Another thing to note is that within Block Store, Dropbox notes that they have a ton of temporal locality, right? So all of the very recently created blocks are the ones that are being accessed the most. If I make a document from a year ago, I'm probably going to access it a lot, the week that I create it, but then a year later, I'm barely touching it whatsoever. Okay, so we're now going to go over the high-level architecture of Magic Pocket. I have a few images here, and we'll just drill down into them. So in Magic Pocket, we've got 3 different zones, at least in Dropbox. Their zones are local to the US in the article that I'm referencing. So they've got a US Central zone, they've got a US West, they've got a US East, and the idea is, we have multiple zones which are a few thousand miles apart from one another, so that if data is corrupted or there's a natural disaster in one of these zones, we can still access it from at least one of the other two. Okay, so what's the architecture within a zone? Because this is where things actually start to get a little bit interesting. So basically, we've got a bunch of front-end servers, right? So these are just our typical HTTP servers, and those are accepting user requests. So if I want to put or get some data, the first place that's going to is one of those front-end servers. Basically, it can go to any of them. They're all pretty much doing the same thing. The front-end server, whether it's a put or a get, is then going to do the same exact thing. It's going to go to this table over here called the block index. Now the block index is just going to be a horizontally scaled out MySQL table, which is going to be sharded and indexed on the actual block hash, right? So every single block is 4 megabytes, but we can take a SHA-256 hash of it in order to get a unique code, and that's going to be the primary key that we use in the block index. That's also going to be the name that we use when we say, hey, get this current block. We're going to provide the hash that we get for that block. So this is useful for a couple of reasons. For one, it can tell us what bucket this block is actually located in. It also is going to map us to a checksum, which is good for performing data validations. As we know, bits on a hard drive can get corrupted or they can flip, and then your checksum is no longer going to match with the checksum, or rather with the actual data block itself. And so that's why having something like this is fairly important. So once we actually have the bucket ID, then what we can go ahead and do is figure out which cell to look in. So the cells are actually where all of this data is stored. We're going to drill down into what those cells are in a little bit, but know that, let's say this thing is in bucket ID 4. I want to go ahead and read it. Okay, bucket ID 4 is in cell number 1. Let me go ahead and perform that read and return it back to the user. Oh, this thing should belong in bucket ID 5. Let me go ahead and, write to bucket ID number 5 in cell 2 and then return a success metric back to the user. It's also worth noting that because the block hash is something that's computed on the actual content of the block itself, if I'm a user and I'm trying to store a block that already exists in Magic Pocket, the block hash existing in this index is going to tell us that that block is already stored and that I'm not going to store any duplicate data. The last piece of this puzzle is that we also have some daemon process over here that's responsible for cross-zone replication. So as I'm writing to data in one of these cells, basically this cross-zone replication process is going to be looking at the block index, it's going to be looking at the cells, and it's going to copy that data from one region over to the other, typically within a second. Okay, now we're really going to be drilling into stuff here when we get to the cell architecture section. So basically, the first thing to note is that within a cell, we want the data to be fairly fault tolerant, right? Because every single bucket that we replicate, we're replicating it within one single cell. So what we do in order to try and increase our fault tolerance here is we try and make failures within a cell unique within power domains. So the way that we do that is we spread things on different racks. So ideally that keeps things separate in terms of both networking and power. But the gist is, so the actual computers within a cell that is responsible for storing this data, different racks, and then we've got a few different components. We've got one master process, we've got a bunch of storage devices, so these are the things responsible for actually storing our blocks. We've got volume managers, which are just co-located on the actual storage nodes. So it's just, like background processes. And they're responsible for moving data around, right? So maybe we see that certain storage device nodes are overloaded and others are more empty. The volume managers are going to be responsible for actually going ahead and moving that data, and then committing that change would happen over here in the replication table, which we'll talk about in a second. Now the thing to note is that these storage devices themselves are very beefy in terms of the amount of hard drives that they contain. So each storage device itself contains about a petabyte worth of disk space. So, you think about that, that could be like 20 hard drives each, and 8 petabytes per rack and potentially 50 petabytes within a cell. They try and limit it to about 50 petabytes within a cell because they find at that point, that's when, having this one single master process becomes an actual bottleneck because you're actually storing so much data and the master has to keep track of all of it. So what is the master actually responsible for? Well, the master itself is also a background process. All it's really doing is listening to these storage devices, trying to determine whether or not they're up or down. And so it's listening to these storage devices, and it's responsible for a few things. Number one is it creates new buckets, right? So we have a bunch of buckets. We're appending blocks into them. We're storing those blocks within the buckets, and eventually those buckets reach their 1 gigabyte size, and they, become immutable. So when that happens, the master is responsible for actually making new buckets. Now, it's worth noting that the master is completely a background process, right? Like, if the master goes down, writes and reads can still happen from this cell. The master has nothing to do with that. That being said, new buckets will stop being created, and so after a couple of minutes, it's possible that we won't be able to write to this cell anymore, and then we're going to have to pick new cells to forward our writes to. The master is also responsible for merging small volumes and performing garbage collection. So like I mentioned, it's possible to delete a block. If we delete enough blocks within a bucket, now all of a sudden that bucket has, a gigabyte of size, except we've basically dereferenced half of it. So maybe we can find another one that also has half of it dereferenced and merge them together in the background. Finally, it's also going to maintain the replication factor per volume. And that's where this replication table comes in, right? So in the replication table, which is again another just sharded out MySQL table where we're using a hash index to keep reads and writes as fast as possible here, we've basically got a list for every single volume which storage devices are actually storing that volume. We also have a little piece of metadata on whether that volume is still being appended to or whether it's completely filled up, so whether it's open or closed. Whether it is a replicated volume or it's an erasure coded volume. Those are two alternatives to one another. I'll discuss erasure coding in a little bit. And then also a generation number. So, for example, if one of these storage devices were to go down, all of a sudden, it's got a bunch of different files on it, or a bunch of different buckets rather, that need to be moved around. So the master is going to wait some time for that storage device to go down. It's going to wait a little bit of time for it to come back up and say, okay, it hasn't come back up, because obviously if it comes back up, it's cheaper to just let it come back up rather than redistribute all these volumes. And then it's going to say, okay, I've got A, B, and C on these devices right here. I now need to distribute them elsewhere. So maybe we've got A on this device, B on this device, and then C on this device over here. It's going to say, okay, well now I need you to copy these to one more node each to ensure that we maintain our desired level of replication. Once it does that, what it'll actually do is it'll take this generation number and it'll increment it by 1. And all of the new nodes that have the new volume themselves have a generation number stored that's associated with that. So let's say the generation number associated with A was 12 before. This guy is going to be storing A with a generation number of 13. What this ensures is that if this guy comes back up, right, and it has A12, we can actually look at the replication table and see which devices we actually expect to have these volumes. And then, let's say the generation number wasn't increased in time, so it never went to 13 because the master went down before it could actually modify the replication table. So we've got, volume to an old list of OSDs, a generation number that still has 12, and then we've got this device with A13 and this device with A12. We actually know that this A13 is invalid and hasn't been committed yet because the generation number here is still 12. So basically, the commit point of when the when the OSDs per volume get changed is when the generation number is incremented and the OSD list is atomically changed at the same time. Now, it's worth noting that the master is a completely stateless process. It operates in the background, and it's only just, hearing from storage devices, and it's only reading the replication table. So even if the master were to go down at some point, we can just bring up another master and resume activity from there. That's why this generation number is useful, is because it acts as a commit point from the master, so that if the master goes down while it's moving volumes around, the new master can take over and say, oh, wait a second, this either went through or it didn't go through, and I have to do it all over again. So I do have this slide devoted to replication details here. I'm going to say everything on it, but pretty much I already did in the last slide, and this is just for the point of being redundant and hopefully hammering down some ideas. So like I said, the master is constantly checking storage to see if they're up. If they're not, we're going to wait a little bit because we would prefer the storage comes back on its own so we don't have to do any data reshuffling. If the storage doesn't come back on its own, we basically need to move its volumes around, and we amortize this cost by basically moving all of those volumes over all storage devices in the cell. Because we have a single master, it makes actually planning out this operation a lot more simple. You can kind of figure out the topology of how much load there is on every single storage device and which network cards are overloaded and whatnot. And so then that single master can make this complicated plan and then execute it after that. Like I said, finally, the idea is our new host specifically, oops, I have my eraser on. Our new host specifically is going to store that volume with its new generation number. So that's going to be one higher than whatever it was before. And the new master is going to commit the operation of having moved this volume to the new host by actually incrementing the generation number in the database, as well as atomically changing which storage devices are actually holding the volume. And so this, of course, is going to be in case of a master failure, right? Because if the master goes down at any point during this, we need to know whether or not the operation has actually been committed. If the master goes down before it can do this commit to the MySQL replication table, then the new master is going to take over and we're going to do this operation again. So another thing to note about the actual, maintaining durability within a cell is there's two ways of keeping data durable, right? We've got normal old replication, which is good. But if we really want to be efficient here, what we can also do is something known as erasure coding. Now, erasure coding probably has to be done some amount of time after the volume is closed, and we'll explain that why in a second. Replication you can do while we're actually, writing the bucket itself, right? As blocks are coming in, you replicate them to multiple different storage devices in the same cell. Erasure coding, you probably need the thing to be immutable. So let's go ahead and talk about that shortly. But I forgot I have this cheeky slide on the put and get implementations within Magic Pocket. So let's go over that quickly. If you recall, because this is going to be more important for this slide, we've got our front end over here. When we're putting data in, all we're going to do is say, hey, does this block already exist? Check the block index. If not, I'm going to go to the cells and say, what buckets do you have open? What can I add to? And then make a decision which one to add them to. So let me go ahead and go back here. We're going to check the block index to see if the block is duplicate. Gosh, my eraser keeps coming back and it's pissing me off. Check the block to see if the block is a duplicate. If not, we go into the cells, we read the replication table, and then we store the block on all storage devices of a particular volume. Remember, we're going to be performing load balancing over cells here. So even though we could go to the same cell every single time, obviously we want to spread this load out. So we pick a cell, we go to the cell, we get ourselves a bucket, and we figure out what actual storage devices the bucket is located on. And then once we have that list, we try and store it all on every single one of those storage devices synchronously. So if there's any single failure for any of those storage devices that we're trying to store this block on, we're just going to completely stop out the operation. We're going to retry with a different volume, and then eventually that write that we had a partial failure on will be garbage collected in the background. So even if our write makes it to 2 of 3 devices, and then this one fails because this device is down, we're not going to count this, and then eventually these writes are going to get garbage collected. As far as gets go, again, the front end is going to go to the block index. It's going to say, hey, for this particular block hash, figure out what bucket it's in. Once we have the bucket name, we can quickly figure out what cell it's in. Once we're in the cell, we can go reach out to the replication table and figure out what actual storage devices the thing lives on, and then we can go read it from there. So when we're actually reading the block, we're going to either read that from a replica, or if it's erasure encoded, we're going to potentially read that a little bit differently. We may have to read from many nodes at once. So let's talk about erasure encoding a little bit more. I keep calling it erasure encoding, but it's just erasure coding. So the main idea behind this is when you have an immutable piece of data, let's say that A and B are each some chunk of data for a block X, right? Let's say A is the first half of the data of the block and B is the second half of the data of the block. If we then write down a third piece of data, A, X, or B, we know that if we have any combination of 2 of these guys, we can always recreate X in aggregate because we used an XOR, right? So it's, you just do another XOR with any 2 out of 3 blocks. So this A XOR B block is called a parity code. The reason it's called a parity code is because it's not the data itself, but it's some operation on the original data such that when combined with a subset of the original data, you can create the entirety of the original data. The reason this is nice is, let's say B goes down. I know that by combining A and A XOR B, I just have to XOR these two guys, right? If I run an XOR here, then I can get B back, and then now I can combine A and B to rebuild my original X. So again, the point is any one of these guys can go down, and we can still create the data of A or B again. Now, this is what's known as a 3,1 Reed-Solomon code, because there are 3 pieces of data that we have to maintain in general. There's one parity code. So basically, there's one piece of data that we wouldn't have had before, but now do have. And because of this one, it means that we're now resilient to one failure. Any of these nodes could go down, and we'll be able to still retain all of our data. That being said, if 2 of them were to go down, we can no longer do so. So the nice thing about this is that think about this versus two-way replication, right? If I have this block X, the idea is that, if I store X twice on 2 different nodes, the amount of storage that I have is 2x. But if I do this with the erasure coding, since A is half the size of X, B is half the size of X, and A XOR B is also half the size of X, that's really just 1.5 times the size of X. And so you're actually saving a lot of storage, and you're still able to tolerate one failure, right? Because in this other situation where we're doing replication, I can only still tolerate one failure. If one of these copies goes down, I still have one full copy left. That being said, on the actual performance side, when it comes to reading the data, now reads must be made for many nodes, right? I have to go and I have to read at least 2 of the nodes in order to get my data back in aggregate. And so this approach in general, this idea of saying, okay, well, we can take the data, we can kind of split it up a little bit, and then we can add additional data known as parity codes, and then, using the original data and the parity codes, we can be resilient to some amount of failures. This can be generalized with linear algebra. So I'm not really going to go exactly into the math, but the idea is you create parity codes that are some sort of linear combination of the original data that you're trying to store. And that way, if any of the original data goes down, you can basically recombine it using some subset of the original data and some subset of the parity codes. So you're welcome to look into Reed-Solomon codes a little bit more. And I think actually in Magic Pocket, they use a different variant of erasure coding called local reconstruction codes, which have slightly different fault tolerance properties. But it's besides the point. When you have something like an NK Reed-Solomon code, it means that you're storing n total pieces of data. So in this case, 3 total pieces of data. You have one parity code, and it means that you are resilient to one failure. So we've actually decreased the amount of data that we have to store while having the same exact fault tolerance guarantees, which is really, really great. Okay, now we're going to go ahead and talk about cold data, because this is another optimization that they use within Magic Pocket in order to basically ensure that they are getting the most out of their disks. So the idea is that cold blocks basically just mean these are blocks that are old and they're no longer accessed very frequently anymore. So in theory, we can have them in a slightly slower variant of storage. And so that's exactly what DropBox does. Basically, they do something very, very similar to our previous slide here, where I explained erasure coding, but across regions, right? Because if we didn't do this across regions, normally we would take our data and we would completely duplicate it in another region. But by doing this, what we can actually do is, again, we can kind of 1.5x the storage instead of 2xing it. Now, I will say that there's a little bit more of a nuance to this when reading the actual article itself, which is they're not technically doing erasure coding across regions. They tried doing that, but the problem is I think that they consider erasure coding like something that they're building their own implementation of. And so what that means is that it's not trivial to erasure code across regions, because it means every single region has to be on the same version of code. And if you're on the same version of code, then now one software bug can take everything out. So they're using a kind of simplistic version of erasure coding, which is actually the one that I explained in the prior example, right? You take a block, you split it into 2. So let's say I have this block A, and I split it into 2 pieces, A prime and A double prime. We've got A prime on US Central, we've got A double prime on US West, and then finally, we'll put in our third region, A prime XOR A double prime. And so that way, when we're actually reading this data, if we need the block for A, all we have to do is reach out to all 3 regions, will formulate the data from the first two responses that we get. So obviously this is going to be slower, right? Because at the end of the day, as opposed to being able to only read from, let's say, our closest region, now we have to read from at least two to formulate our response. That being said, when they actually do experimentation and test out how slow this thing really is, it's not that much worse than single region latencies, especially in the 99th percentile, because the 99th percentile of a single region read is, the single region like completely craps out on you and then you have to retry and maybe go to another region. But this is pretty much already trying three regions where only two of them have to succeed. So even if one of the three regions is being super slow, you'll actually already have basically prefetched the data from two regions. And so it's not too slow overall. And then, of course, within a region, we're still doing replication of, this A prime or this A double prime, and we're still doing erasure encoding to ensure that we have fault tolerance within a region as well. Cool. The last thing we're going to talk about is SMR disks. So I don't really have too much information to provide here because at the end of the day, I'm not a hardware guy, but I did want to talk about this because I still thought it was kind of cool. Basically, your normal hard drive that you use probably 99% of the time is known as a PMR drive, where the P stands for perpendicular. The reason it stands for perpendicular is because you can do random reads and writes. So like if I'm a disk head right here, the penis thingy, I can jump from here to here. And maybe I can jump back here, and maybe I can jump back here, right? We have multiple different tracks of disks, and I can jump between them. In an SMR disk, it kind of looks more like a spiral, where like you've got this track, and it almost overlaps with itself. And so what it really means is that like the disk head can only progress along the track, and you pretty much always have to do sequential reads and writes. That being said, if you're only going to do sequential reads and writes, you can actually take advantage of the fact that this SMR disk is a little bit more space efficient in terms of how it lays out these tracks. And so that's what they do in Magic Pocket. It's kind of a footnote compared to what we're interested in this channel, but I thought it was kind of interesting nonetheless. Oh, and then one final point I would like to touch upon is that we're doing erasure coding, and we say, we're going to do reads for many different nodes. That's true, but one optimization that they actually make within Magic Pocket is that even though we're doing erasure coding, one of the nodes will still store the entire block in its entirety, so that in theory, at least if that one is up, you can have faster reads. If that one goes down, then you'll have to actually do the normal erasure coding read where you kind of recreate it in aggregate. Sorry, I had to make that footnote. Wouldn't want anyone to forget that. All right, so let's go ahead and conclude this thing because my voice is starting to get a little bit tired. Basically, I have been looking for multiple years now to try and figure out how something like S3 is built, and I simply have not been able to get any good information there. ChatGPT, as you might expect, is useless, Amazon is useless, and it never really occurred to me that there were other companies that were also making object stores at this large of a scale that were maybe a little bit more honest about how they did it. So, Magic Pocket is going to do that for us. It's very simple, right? They're not using any sort of coordination or consensus protocols. They're just doing strong consistency. If writes fail, it's totally fine. Just go ahead and clean it up later. It's not a big deal. They've got stateless masters per cell so that the master can go down, and then they'll just go ahead and replace it if so. Having a single master allows the master to make tough decisions, or rather, have one unique view of everything that's going on, right? If we had multiple different masters and we were trying to re-replicate things, and we were, making the plan on how to do the re-replication, they would have to synchronize their state over the network, and that would be tough. In terms of durability, obviously we care about replication, erasure coding, and geo-replication. I believe they're going for many, many nines on this one, and so, they have no choice but to do all this stuff. Obviously, they care about scalability. The whole point of this thing is to be as cheap as possible while also expansive and storing literally exabytes of data. So you can always add more cells, right? That's kind of their unit of scalability. They say at some point, having a single master is going to become a bottleneck in a cell. So rather than adding more masters, just add another cell. They've sharded all of their MySQL tables, so those are all horizontally scalable. And they've also made their front-end servers horizontally scalable within a region. Finally, they're also very, very concerned with disk efficiency and storing the minimum amount of data possible on the most efficient disks possible. So they do that by using SMR disks. They perform erasure coding so that once data becomes immutable, it is less expensive to store it all. And then also they do that concept of cross-region block splitting that we explained over here for cold data. so that rather than storing a complete copy of the data in another region, now we only have to store, basically 75% as much data. Anyways, guys, I hope you enjoyed this video. There's some pretty interesting techniques and tricks that are used in a system like this, which I wouldn't really have known otherwise, because it's not like we have to study like the actual storage of objects all day. But nonetheless, I think it's very interesting, and I feel like it was a very insightful series of articles. So I hope you enjoyed this one, and I will see you in the next one.